So we're going to continue trying to find confidence intervals for a population proportion. And what that's going to mean for us moving forward is that we're going to use a lot of technology, but I'm going to put more emphasis on interpreting your answer and interpreting it correctly. So, for example, B here, let's take note of the important things we need out of this. A drug is used to help prevent blood clots in certain patients in clinical trials. Amongst 4,584 patients with the drug, 189 developed the adverse reaction of nausea. Construct a 99% confidence interval for the population proportion of adverse reactions. So, all right, we want to find a confidence interval. And I wrote down all the stuff that I highlighted here. So N and X and 99% confidence. So just for practice, if we have a 99% confidence level, 99% equals 1 minus alpha. Or in other words, alpha equals 1 minus 99%. What's alpha equal? Without
0.01.
Perfect, 0.01. Just so you know, so that's your level of confidence. We're going to find a 99% confidence interval, but on the other end, alpha is 1%. You should be able to find things like Z alpha over 2 using the proper Google Sheet command or statdisk or your graphing calculator. But for now, hey, we're going to use statdisk. So let's make our life easy.
Wait, I have a question.
Yeah, please.
Will N always be the bigger number?
Yes, it has to be, because your proportion of successes cannot be any bigger than the number of trials. So this is the number of trials. So the number of successes can't be bigger than the number of trials. So this is always going to have to be the bigger number.
Okay, thank you.
Yeah, no, thank you. That's a good question. So let me go back here to statdisk. Fortunately, we're already here. Just as a quick reminder, you get here by going underneath the analysis tab, confidence intervals, and then you want proportion, one sample. So the default is a 95% confidence interval. We want a 99% confidence interval. That's going to make it wider than if we left it at 95%. 4,584 was our sample size, and of those, a mere 189 actually became sick with nausea. So type all those in, press enter, and wow, look at how small your error is. It's less than 1%. So that means you've got a really narrow confidence interval, despite everything. You've got a very narrow confidence interval, and that's good. You want to know where the true population parameter is. And if your margin of error is less than 1%, that's going to mean this is really small. So let's write down those numbers. So our 99% confidence interval is between 0.0337 and 0.0488. Now that's just numbers. And because I'm making it very easy for you to get these numbers, I am going to ask a little bit more of you, and that is this. I want you to interpret this. So you can pretty much copy exactly what I'm doing for all of your confidence intervals. We can be 99% confident that the true proportion of nausea is between 0.0337 and 0.0488. I probably wouldn't mind if I put in true population proportion, because that really reminds you that this is just an estimate, you know, the proportion that we get here. In fact, it is kind of a little bit of a drawback of using statdisk, is it doesn't really tell you what p hat is. P hat is our point estimate. And that's going to be 189 divided by 4,584. So about 0.041 or 4.1%. So it's odd that it doesn't tell you. I mean, statdisk is great, but I think it's strange that they don't give you that proportion. Yeah, it wouldn't be hard, but it's not hard to get it either. Now we know that if we took another sample, we'd probably get a different sample estimate. That variability is why we surround it by a confidence interval and say, you know what, it's probably in here someplace. The true proportion of people that would experience nausea on this medication. Okay. Make sure you can interpret it in words. One thing to be sure of when you're doing that is do not use the word probability here. Do not use the word probability. Probability associated with that is not what you would expect. It's not 99%. It's not 1%. It's either 0 or 1. This contains the true population proportion or it doesn't. We don't know which, so it's a 0 or 1. So if you want to use the word probability, you have to be really careful. I would suggest you avoid it completely. Just talk about the level of confidence. Now, what that level of confidence means is that it's confidence in our procedure. 99 times out of 100, this procedure will contain the true population proportion. Sometimes it won't. Now, if we look back at what we did with our estimating the proportion of Earth's surface covered with water, we can kind of see some of that looking back. Now, I took the time for my morning classes to look at the confidence interval for each of their estimates. So like DK here had a confidence interval between, say, 61% and 81%. That holds the true population proportion of 71%. But there's some that don't. Like this one. That doesn't hold 71%. This one's close, but no cigar. These two, way, way low. Yeah, okay. You know what? What that level of confidence is confidence in the procedure, that when you do this, 99 times out of 100 or 95 times out of 100, whatever your level of confidence is, this interval will contain it. Now that's moving forward into the future. It's not once you've done the experiment. Once you've done the experiment, once you've got your data, this either contains it or doesn't. There's no more probabilities associated with it. So write your conclusions just like we did there. Let's move to example C. A genetics experiment with peas resulted in one sample of offspring that consisted of 445 green peas and 154 yellow peas. Construct a 95% confidence interval to estimate the percentage of yellow peas. So, okay, let's write down a couple of relevant things here. We've got 445 green peas and 154 yellow peas. And we want a 95% confidence interval. Okay. Well, I need to know what N and X are. What's N for us?
445.
Actually, this one's a little trickier.
I'd say it would be 445 plus the 154 because it's the population of all the peas.
Yeah, so this total is the total number of samples that we took. So it's 599. So it's a little tricky, and I'm sorry. I hope I didn't really mean to trick you there. So that's your total sample size. How many successes did we have?
154.
Yeah, 154 of them were yellow. So your proportion of successes is 154 over 599, so a little bit less than 26%. Let's see here, 154 divided by 599. Oh yeah, 25.7%. So 0.257. All right. And we wanted a 95% confidence interval, so that's pretty easy. In fact, this whole problem has gotten a lot easier because now we're just going to go to statdisk and type in the data. We need to change this to a 95% confidence level. 599 trials, 154 of them were successes, and bam, there you go. So our confidence interval is somewhere between 0.223, I'll call it 0.224, and 0.294. Okay, how's that looking? You all right with that?
All right, so it's the Wilson score confidence level we want to use and not the...
Oh, you know what? Did I grab the wrong one? No, I wanted to grab this one.
Okay, all right.
No, it's always this one. We're not going to use the Wilson one. I think that might be a non-parametric version. I'm not sure. But no, my bad. So I appreciate you correcting me. We're always going to use the top one there, Andy. So 0.222 to 0.292. Yeah, 0.222 to 0.292. So the width of this is exactly, I think, 7%. Hey, you can see our margin of error is 0.035. So a 3.5% margin of error. So let's write that down. E is 0.0350. That's just good to know. That's your margin of error. And now I need to write a conclusion. Now I'm going to write a conclusion just like I did up here. We can be 99% confident that the true population proportion of nausea is between this and this. All right. You're going to do it kind of in a cookie cutter fashion. Start out by stating the level of confidence. We can be 95% confident that the true population proportion of yellow peas, and I like that we refer back to what we're talking about. I mean, I don't want it too cookie cutter. You should tell the reader what you're actually talking about. The true population proportion of yellow peas is between 0.222 and 0.292. There you go. And then you could write it as a percentage if you wanted to. 22.2% and 29.2%. That's fine. So,
get out there at 9:15. It just depends.
Okay. Yeah, that's pretty much what I would like from that. So, how are we looking on that one? All right. There's a little bit of background noise, so I muted everybody, but you're free to unmute and respond. This is exactly the kind of thing that I want. Now, you might not get that too much on this next test, but you will on future tests. Okay. Let's continue this way. So any questions before I move on from example C? There's a couple of little things we got to cover before I let you go here. Now, staring me in the face for the last several weeks has been a bag full of data. And finally, this morning, I broke out the data and did a little counting. And so let's go through the results. Yay. So, yeah. Now, I really regret being not being in class at this point because usually I have my students do this stuff. In fact, I've got some data from previous students here in terms of each column is, you know, a bag of M&Ms I passed out, et cetera. But here's my data from this morning. And I added that up to all this other data that I had from last fall to get these totals here. Now, let's focus in on one of the colors of M&Ms in particular, and that would be the green M&Ms, which I think is this row right here. Yeah, those are my green ones. Now, in case you're not familiar with it, and I'm not going to dwell on it too much here, but the kind of fun urban legend about green M&Ms is that they're an aphrodisiac. So, whatever. You know, you can do a fact check at Snopes to find out if that's really true or not. But for at least my generation, it was always fun to think about the green M&Ms. Now, what I'm interested in is this. I want to look at my confidence interval. So let me go over here. And here's my confidence interval for the population of green M&Ms. So right there. Now, it actually does contain the true proportion that you get out of Mars. Mars will tell you that, you know, from their Cleveland plant, and I think that's Cleveland, Tennessee, from their Cleveland plant, 12.5% of their M&Ms should be green. Now, I got a confidence interval somewhere between 0.043% and 2.32%, or 0.232, or 23.2%. So not really all that narrow, which is kind of a bummer, but that's okay. We can use that information as part of a problem. So let's take a look at the calculation of P hat and E. Calculation of P hat and E. Now, using my numbers from the previous page there, they were 0.043 and 0.232. Those are the endpoints of my confidence interval. But I could ask for some things like, well, what's P hat? What's Q hat? So let's figure that out. All right, so we had 0.043 and 0.232. And this is going to be p hat minus e and p hat plus e. Well, I want to figure out what p hat is. And p hat's going to be right there in the middle. So, how am I going to figure out that when all I've got is these two? Any ideas? Nothing?
Would you add them up and divide by 2?
Nice. Perfect. Basically, you're going to take the average. So if we add them up and divide by 2, then that should give us what's in the middle, the midpoint of this, which is exactly what we want. So p hat is going to be the middle. And let's do that here. P hat would be 0.043 plus 0.232 divided by 2. So that's going to be 0.275 divided by 2 is 0.01375. Yay. So that's p hat. But what about E? You could be asked for E. And there's a couple ways you could get E. You could do P minus this number here. You could do this minus P. Or you could realize that the width of this interval is twice E. So let's do it that way. Twice E is going to be 0.232 minus 0.043. So that's going to give me 0.189. And if I divide that by 2, it's going to be 0.0945. Yeah, there we go, 45. So that's E. So you can reverse engineer these things if you need to. That also gives me another way to write this if I wanted to. If you were given this, sometimes you're asked to write it like this, p hat plus or minus E. So now you could write it as I think I got an extra 0 here. Yeah, that decimal should be there. So you could write this as 0.1375 plus or minus 0.0945. Beautiful. So now you can switch between one form and the next. You can go from this form, p hat minus E, to p hat plus E, which for us was 0.043 to 0.232. You can start out here and go there, or vice versa. Are we okay with that? There is kind of a big drawback, though, in my estimate for the proportion of green ones. That's kind of large, right? I mean, if you take a look at my interval, somewhere between 4% and 23% of M&Ms are green. That's a big range. I mean, you're not really telling me a lot by saying, oh, the proportion is, you know, somewhere in an interval that's almost 20% wide. It's a big interval. So sometimes you might want to shrink that interval. And the only thing we can do to shrink that interval is collect more data. And that is have a bigger sample size. So that's what we're going to do next is we're going to calculate the sample size necessary so that I can make this error term as small as I want. So let me do that. Now for that, you're going to need a couple formulas on your sheet. And there's 2 formulas. I'll do an example of each of those. What you're going to find it here is here's the problem, and then on your handout, you'll see it down here for your sample size calculations. Now there's going to be 2 possibilities. One in which you know some information about your sample ahead of time, and one in which you don't know some information ahead of time. So let's look at example D here. It says, you're the operations manager for an airline. You're considering a higher fare level with passengers in aisle seats. All right, I'm thinking that it's not a good idea to do in the current climate of travel, but how many randomly selected air passengers must you survey? Assume that you want to be 99% confident. So let's write this down. This is example D. And for part A, I want to be 99% confident. And I want an error of 5.5 percentage points, so that the sample percentage is within 5.5% of the true population percentage. Remember, that's what we're always trying to estimate, is this true population parameter. And this section is percentage. So if we want to be within 5%, 5.5%, then how many samples should we draw? Well, that's where we need our sheet here. Now there's two cases. In the first case here, part A, this is assume that nothing is known about the percentage of passengers who prefer aisle seats. So we got nothing. And that actually kind of makes the calculation a little bit easier. We're going to use this second formula when no estimate of p hat is known. And that means you're going to need this information right here. Well, all right. Let me write down one more thing here from the problem, and that is E is 5.5%. So E is 5.5%, but you better write that as a decimal if you want to put that into your calculator or something like that. If we want to be 99% confident, that means 1 minus alpha is 0.99, or alpha is 1 minus 0.99, or 0.01. You may have noticed that part of that formula was to find z alpha over 2. For that level of alpha, let's figure out what z alpha over 2 is. That's going to be z sub 0.01 over 2, which is z sub 0.005. I think we found this value earlier, but I'll remind you what it is and how to find it. That was a good one. That's a good distribution. So what I'm looking for is the point with that much area in the right tail. So just this little bit here. So it's going to be z sub 0.005. That much area in the right tail. Well, if that much is in the right tail, how much is here the rest of the way? Well, it'll be 1 minus 0.005, which is 0.995. So if you're using this off of Google Sheets, then what you'll get, or what you can write, is equals norm inverse of 0.995, comma 0, comma 1. And I'm not going to take the time to do that here. You can trust me that it's about 2.575. So I think I've got everything I need now. My formula for this part was n equals z sub alpha over 2 times 0.25 divided by E squared. So let's start filling things in. Z sub alpha over 2 is going to be 2.75. That should be squared. Divided by E squared, and E was 5.5%, so 0.055 squared. Let me do that on the calculator. So I'll clear out all this mess. So 2.575, and then hit the square key. And I guess what I like doing it on the emulator here is that the last key that I hit remains highlighted, times 0.25 divided by 0.055, and again, hit the square key. So I get 547.98. Now the thing about these calculations is that you always round up. No matter if this is 0.98 or 0.09, you always round it up. So always to the next highest integer. Round up. So about 548 would be your sample size requirement. All right. How are we looking on that one?
So you would like us to round up to the nearest whole number on
Yep.
the on all of our assignments?
Yep,
All right.
always round up. Now it's a little different than, usually you round symmetrically, right? I mean, 0.5 and more, you round up, 0.4 and less, you round down, that kind of thing. But these, you always round up.
Okay.
So you
Right.
use this formula only when you don't have any information for P, right?
Exactly. Now there's a part B that says, you know what, we do have a little information for B. So I'll look at that in a second. But are we okay with part A here? Okay. Let's take a look at part B. The difference between part A and part B is part B says, you know what, I forgot. We actually do have some information. So let's highlight that information. It's right here. So to assume that a prior survey suggests that about 36% of air passengers prefer an aisle seat. So, okay, that's going to change our calculation because we're going to use a different formula this time. So this time we use this formula right here, where we know P hat, we've got an estimate for P hat. P hat in our case is 0.36. So I'll write that down along with our new formula. So P hat is 0.36. By the way, can anyone tell me what that makes Q hat equal to?
.64.
Thank you, 0.64. Now the formula we're going to fill in this time is going to be n equals z sub alpha over 2 squared times P hat times Q hat divided by E squared. Now, a couple of these things aren't going to change. So Z sub alpha over 2, that's still going to be 2.575. P hat is still going to be 0.36. Q hat is still going to be 0.64. And actually, you know what? I shouldn't say still. In the previous calculation, this was 0.25. Now I've got it as 0.36 times 0.64. But the denominator is still the same. It's 0.055. So why don't you see if you can't calculate that sample size? And it should be lower than what we just got. So let me clear out this. And clear that out. 2.575. And then hit the square key times 0.36 times 0.64 divided by 0.055. And again, hit the square key for that. What'd you guys get?
I got 505.023.
Great, 505.023. Someone tell me how I'm going to round that. Does that round down to 505 or up to 506?
506.
Well done, Joe. 506, yeah. Even though it looks ridiculously close to 505, you're still going to round these up. That's because you're being a little bit more conservative. You want to make sure that you get within your 5.5% error. So that's why you round up with these calculations. Okay. Let me go back and cover a part of a question that I didn't really answer when we went through it. And let me see if I remember. Yeah, it was back to example C. There's a little part of example C that I didn't answer, I think. So let me go back there. Example C. So we got an nice confidence interval. And our confidence interval was this one right here, between 22.2% and 29.2%. But the part B says it was expected that 25% of the offspring P's would be yellow. Given the percentage is not 25%, I think we got 25.7%. Do the results contradict expectations? Well, do the results contradict expectations? And like I said, just a minute ago when we did this calculation, we ended up with 25.7%. So does that mean this idea of 25% is wrong?
I don't think so.
The thing to notice is that that 25% fits inside this interval, doesn't it? Because remember, we just got one estimate. That's your point estimate. But when you look at the confidence interval, your confidence interval contains that 25%. So it's not a contradiction. Doesn't contradict what was going on with that one. So nice. Now, let's see here. I'll try and be real brief about this because there's a debate tonight. And in the last debate, one of the combatants, is probably a fair way to say that, misquoted the study that I sent to you. And it's this one right here. You can look it up. It's fresh off the press, came out last month. And basically you had cases and controls. These are people who reported for a COVID test because they thought they had symptoms. And they said, oh, let's collect some data on you. And there was a couple interesting things that came out of this study. First of all, the proportion of people that reported using a mask was about the same in both the case group, people who had COVID, and the control group, people who didn't. So you're like, oh, well, why should I always wear a mask? Well, if you think about all these different behaviors here that you could expose yourself to, the one behavior that absolutely means you're taking off your mask is being in a restaurant, right? So, and what I did here for us was I calculated a couple confidence intervals for people who ate at a restaurant amongst the case group and people who ate at a restaurant amongst the control group. And so let me share those calculations with you. I hope that you're pretty comfortable using those or getting those off of statdisk. So here was amongst the cases, somewhere between 33% and about 49%. So we'll say I'll do it this way. So somewhere in here, 33% to 49%. That's what my confidence interval is saying. Now, if I take a look at the control group and look at the percentage of time they had been in a bar or restaurant the previous 2 weeks, it was somewhere between about 21% and 34%. Now, as a statistician, I'd like to say that these groups are statistically different, but are they? There's a little bit of overlap here. So there's a value of the population proportion that could be true for both groups. Now, this is a very weak way to analyze this, but I just chose this because it's relevant to the world we're living in, and it's also relevant to our stat class. But with better methods of analysis, you can show that it seems like being in a restaurant, and I'm not going to be in a restaurant, so I really miss it, but being in a restaurant puts you at greater risk for having COVID. So, that's what it's just saying here. Now, the paper actually does conclude that very thing, but the analysis here can't do that because we don't have quite the sophisticated methods that we need yet to do those kind of things. We can later, though. All right, let me finish up by reminding you that you've got a test coming up this Tuesday, and let's see here. There we go. So the test is really a good chance for you to do well on an exam because it's only going to cover 5 sections, 6.2 through 6.5, and what we just finished covering, 7.1. You should be prepared to find areas underneath the normal curve, a non-standard normal curve. The last test we did the standard normal curve. This test, it's the non-standard normal curve, or just any normal curve. Also look for areas, or you look to be given an area and find the corresponding value of X. So you're going to be using norm inverse or inverse norm, those calculations. So here's some examples of those kinds of problems. Not too much that I'm going to hit you with from section 6.3. You might want to look over your homework. But the one thing I have, said about the section, know which estimators are biased, know which ones are unbiased. Central limit theorem, we did a lot of problems there the other day from section 6.4. So expect some problems like this from the book. Now, when I say problems like this, 7, 11, and 12, this isn't from your homework in terms of the homework on my math lab. But if you look up the text, if you open up the e-text, you can turn to page like 276 or something like that, whatever it is, at the end of section 6.4, and look at the problems that are in the book. And these are the kinds of problems you should expect. Section 6.5. I discussed the other day 4 different methods of how to decide something is a normal distribution. What are those methods? You remember? What's like the first easy way to decide if something has a normal distribution? Make me look good. One more time, Rebecca.
A histogram.
Histogram. Perfect. What else? I kind of gave it away a little bit. What kind of a plot does it?
A quantile plot.
Yep, normal quantile plot. Thank you. If there's at most one outlier, okay, if there's more than one outlier, then chances are it's not a normal distribution. And this you can get from statdisk. It's your Ryan Joyner test. Of course, last but not least, the section we just finished up, find confidence intervals, do sample size calculations, and this is more for tests moving forward. I don't know how I'll test this too much on the next one, but interpret your confidence interval in words. Definitely make sure you get comfortable with the language that I talked about there. We can be 95% confident that the true proportion of green M&Ms is between 4% and 23%, that kind of thing. All right, do not use the word probability in stating those things. Whew. All right, go get an A.
All right. And will it be on the math lab or will it be in some other link?
I'm working towards making it a test in my math lab.
Okay, just wanted to make sure. I know you were talking about that, so
Yep.
I'll
Thank
watch
you.
for the email then.
Yep.